Today we're going to continue learning techniques for finding limits as x approaches value of a function, and we're going to expand what that value could be. We've always considered x approaching a real number. By the end of this, you'll learn how to find limits when x is approaching infinity or negative infinity. And first, let's recap the types of techniques that we've learned so far, right? If the first thing we always try to do in finding a limit is just plugging x equals a into f, right? And if we get it a number, then we're done. If we get a non-zero number over 0, then we know that we have an infinite limit, and we have to break it down into its left and right hand limits and calculate each of those to see exactly what's going on. And if we get 0 over 0, then we have something called an indeterminate form. And we need to go further either by factoring or by multiplying by the conjugate. In the case of square roots, multiplying by the conjugate of the conjugate, then factoring, then plugging in, right? Now, I've been sweeping a little bit under the rug when I say, oh, you can just plug in x equals a. Why can you do that? Well, you can do it because of these things called limit laws. Here are the first 5. There are others, but these are the basic ones. And they basically just say that, whether you take the limit of each, like if you've got, for example, f of x plus g of x, and you want to find the answer, it doesn't matter whether you take the limit of the whole thing or whether you plug x equals a into f of x and then into g of x and take the limits separately. Right, but these are the building blocks for everything that boils down to our saying you just get to plug in a and the limit works out. And I want to show you an example of this, right? Suppose we have something basic like this. Find limit as x approaches negative 3 of x squared plus 9 over x minus 4. Now, normally, without limit laws, we would just say the limit as x approaches negative 3 of x squared plus 9 over x minus 4 equals negative 3 squared plus 9 over negative 3 minus 4, which winds up being 18 over negative 7, or just negative 18/7. Done. That took us about 10 seconds. With limit laws, maybe I'll actually even maybe I'll even just change the color of this to red. Yeah, something like that. There we go. Right. So that's what we're dealing with. Just to point out that that's not what we're trying to do here. Right. With limit laws, we have to say, okay, the limit as x approaches negative 3 of x squared plus 9 over x minus 4, I'll make that clear that is a 9, is, okay, well, first off, we have a limit of a quotient, right? And so the last limit law, right, number 5, says that, well, I guess this is the same as the limit as x approaches negative 3 of x squared plus 9 over the limit as x squared minus 3 of x minus 4, and this is provided that we don't get an answer of 0 on the bottom, which we know we're not going to. And then further, we know that the numerator, again, using limit laws, I'll just write LL to denote limit laws, equals LL just for limit laws. This is the same as the limit as x approaches negative 3 of x squared plus the limit as x approaches negative 3 of 9. Divided by, and we do the same thing on the denominator, right? Limit as x approaches negative 3 of x minus the limit as x approaches negative 3 of 4, right? And this is just limit laws numbers 2 and 3. Right? And then we can go even one step further and say, well, again, using limit laws, I guess in this case number 4, we have the limit as x approaches negative 3 of x quantity squared, right? Because, right, we've got this x squared right here. And so, again, look at limit law number 4. It says that the limit of the product is the product of the limits. And then, again, we can just keep this the same. You could take the limit. We know it's just 9. And, again, this is going to be the same. x minus the limit as x approaches -3 of 4. And now, finally, well, you can say, like, well, okay, we know that as x approaches -3, x approaches -3, right? And so we have -3 quantity squared, again, from that limit law, plus 9, and then this is divided by that. And then this is going to be divided by -3, and we know x approaches x minus 4, and then that's how we're getting our 18 over -7. So here's my question. Which would you rather do? Just plugging it in and being done with it, or using limit laws? Yeah, exactly, right. Plugging it in is so much easier. But we have limit laws because that's what allows us to just plug it in. We had to do all this and make all these observations to know that, oh, okay, we're really allowed to just get away with doing that. Okay. Let's go ahead and do example 3. I actually don't really need to use limit. Let's cancel out using limit laws here. This is a little bit just sort of out of left field, but it's one more indeterminate form that I want to get into. And that is infinity minus infinity. Okay? So just hold on to those limit laws for a sec here. We're not going to use them right now. But let's just take a look at one more type of indeterminate form. If we try to plug in 0, we're going to get infinity minus infinity, right? Because 1 over 0 is infinite, right? That's what we were talking about before. We get infinite limits when we have a tiny denominator. But we have infinity minus infinity. Now, you might think the answer is 0. Oh, it just cancels itself out. But that's not really correct. Because each of these terms, right, this guy and that guy, might not be approaching infinity at the same rate. And so their difference might not be approaching 0. So this is another type of indeterminate form. Okay. So instead what we do is we have to, well, simplify it in some way. Let me zoom out for a bit, maybe a little bit more. And what we're going to do is, well, what do we do when we add or subtract fractions? We need a common denominator. And in this case, it's not quite, I mean, it's not lovely, but like all we need to do is multiply by one term, square root of 1 plus t over the square root of 1 plus t. And now we can write the expression after the limit thing as just one fraction, right? 1 minus the square root of 1 plus t. All over t root 1 plus t. Or yeah, just over that, right? It's just the same denominator, so just write it as 1. Right? That's the nice thing about getting a common denominator. You write it as one fraction, you're done. Okay, so now let's plug it in. Now when we plug in t equals 0, you might notice we get 0 over 0. Well, not great, it's another indeterminate form, but at least it's an indeterminate form that we're familiar with and one that we know how to handle. Right? So in this case, we're going to multiply by the conjugate. Remember, same rules as before. Please do not simplify the bottom. And anyway, we're going to get 1 minus the quantity 1 plus t squared. No, sorry, not 1 plus t squared, just 1 plus t. Right, don't square it. But note that we got rid of the radical, and note that we are subtracting the quantity 1 plus t. Please remember those parentheses. Okay, so now we have this. And I think we can do a little bit of simplification. And we're just going to get 1 minus 1 minus t. Be very careful about that minus sign. Right? Please don't write plus t. That would not be correct. Okay? So anyway, at the bottom, we get this nonsense once again. Let's cancel. And then at this point, note that we have a factor of t on the top. Let me use a highlighter for this. A factor of t on the top, t on the bottom, right? Because we're still getting 0 over 0. Right, just like we always do when we multiply by the conjugate, right? So this is what we now cancel. I'll use green to cross it off, right? And we now have -1, right? Just be careful about that negative, right? So anyway, we have the limit as t approaches 0 of -1 over all this. Then at this point, we plug it in, and we get... Right, at this point, you could do all the limit law stuff if you want, the limit of the square roots, limit of the square root of the limit, blah, blah, blah. But anyway, you get -1 over 2. And that is your answer, okay? So that's just another type of indeterminate form, right? So just want to recap, we have 3 indeterminate forms. Right, we have 0 over 0, meaning we need to factor. 0 over 0, meaning we need to multiply. Well, multiply by conjugate. Right, it's still 0 over 0, but it looks different. And then we have infinity minus infinity, and that implies use a common denominator. Okay. Anyway, we're now going to go to limits and infinity, and now we're going to remember those limit laws, right? Now they're going to be helpful, right? Now that we're done with these, looking at the 0 of 0 indeterminate forms. What if we look at something like example 4? Find the limit as x approaches -infinity of this bad boy. Well, be a little bit careful because it looks like the top is approaching infinity. Negative infinity, actually. All right, 4x cubed plus 6x squared minus 2 all over this guy. Right? The top appears to be approaching -infinity, right? Because as x gets really, really large, we're concerned only about the leading term, right? Because cubing a large number is so much bigger than squaring a large number. It doesn't even matter what the coefficients are. These terms are effectively irrelevant. And this is going, because the degree is odd, and x is approaching a negative, we're going to -infinity. The problem is, if we look at the bottom, well, then we're approaching positive infinity. Again, we don't care so much about the leading term. Actually, let me not cross those out. I don't want to, forget about them. But the point is that we're concerned only with these guys, right? Only with these guys. And maybe I'll use this. These guys are not really relevant to the situation. We don't want to forget about them, but they're not going to help us solve the problem. So anyway, we have a situation where we have negative infinity over infinity, and that's not a thing. And you might think, oh, it's -1. No, it's not, because the top and bottom might increase at different rates. Okay, so this is yet another indeterminate form, right? A little different from what we're used to seeing. So we have to approach it a little bit differently. So what we're going to do in this case is we're going to use limit laws. Remember, I said they would help us with limits at infinity. Here we go. Limit laws apply only when our limits exist, which means only when the limit is a real number. Right now, the top and the bottom limits are infinite, so they're not helping. So what we're going to do is we're going to divide out by x to a power to make at least one of these things exist. And in this case, we're going to divide by the lower degree leading term, which in this case is 1 over x squared. Let me blue that up. Right, and so when we do this, we're going to actually get kind of a nasty looking thing because it's going to be a bunch of repeated fractions, right? 4x, that's not so bad, but it's going to end plus 6, that's not so bad. But then it's minus 2 over x squared. And that's not very pleasant to look at. The bottom is even worse. 2 is kind of nice, but then we have minus 4 over x plus 5 over x squared. Yuck, I can't stand repeated fractions. However, we need them. And promise you we won't do any crazy arithmetic with them. Now, we can look at this and say, okay, hold on a second. The denominator is approaching 2 minus 0 plus 0. Do we see that? Because 2 goes to 2. Negative 4 over x is actually going to go to 0, right? Because as negative 4 stays the same and the bottom, the denominator, gets big, the fraction gets really small. A similar thing happens with 5 over x squared. Now, a similar thing actually happens with, I guess I would say, negative 2 over x squared, right? It's also going to go to 0. 6 is going to go to 6. And the question really becomes, what is happening with this 4x? Well, x gets really large without bound. Everything else goes to 0 or just a constant, right? 6 is like, and sort of in 2 land, right? And 4x blows up, but in the negative direction, right? Because x blows up in the negative direction, and we just multiply it by 4. So this equals negative infinity, right? We have a negative divided by a positive, which gives us negative, and we have negative infinity. So that's our answer, negative infinity. And we needed limit laws, right? We needed to multiply by this 1 over x squared over 1 over x squared. If we didn't do that, then I would not mark it as correct. I would maybe give you like 7 out of 10 or something. But it would not be fully correct because you can't just reason, oh, well, the top infinity is bigger than the bottom. We have to use limit laws to show that. Okay? Here's one more example, right? A little bit different. Same sort of thing. We're going to need to use limit laws. Still have a limit as x approaches infinity. Let's bust out that purple again. But it's still not a fraction. Right, and this is another type of indeterminate form. We've kind of seen it before, actually. It's infinity minus infinity. Very weird, right? A weird one. This is just sort of a weird one. Turns out the way to do this guy is just to multiply by the conjugate over the conjugate, right? Hardly knew ye. And so in this case, when we do that, we take something that looks, I don't know, not all that bad, and we make it look a bit worse. But it's more manageable, right? Because multiplying by the conjugate over the conjugate tends to solve our problems, right? And so even though we created a fraction out of nothing, we still have something to work with, right? Let me just rewrite this, because this could look a little complicated. Now, at this point, it may not be entirely clear what to do, right? Because we still do have an indeterminate form of infinity over infinity. But what we can do is we can multiply the top and the bottom by 1 over x, right? The x in the top is what's messing with us, and frankly, the x in the bottom is messing with us too. So let's get rid of it. Remember, if we can make our limits numbers, then we can use limit laws and find out what this limit is. Okay? So we're going to get, well, I think the top is easy enough. We just get 1, right? Because x divided by x is 1. The bottom is less clear. Let me do the bottom over here. The square root of 9x squared plus x all over x is the same thing as the square root of 9x squared plus x over the square root of x squared. And radicals work nicely with division and multiplication, so we can just kind of make one radical. And when we do that, if you think about the fractions, right, if we just split up the fraction, we get 9x squared over x squared plus x over x squared. And then this becomes the square root of, well, 9 plus 1 over x, right? So I'm going to just take that, highlight it, and stick it right here. Whoop. Stick it right here. All right, we've got this. Well, maybe not that, but yeah, I guess I could say this divided by this became this. Right? Okay. Anyway, we are also dividing 3x by x, but that's pretty straightforward. Just get that right. And now at this point, we can plug in infinity, so to speak. We technically don't plug in infinity; it's not a number, but we can imagine x increasing without bound. 1 over x goes to 0, so we get this 1 over the square root of 9 plus 0, and then plus 3, and then this winds up being 1/6. And that's our answer, 1/6. Again, we needed limit laws, right? This is where we use limit laws. Okay. All right, a couple other little loose ends here before we head out. Just kind of throwing this in, just keep it in the back of your mind. There's this number e that's extremely important in calculus. It's roughly 2.718, whatever. Just keep it in the back of your mind. It's defined using a limit at infinity. So, just kind of wanted to define it right here. What's the limit as x approaches infinity of e to the negative x? If this is weird to you, just write the limit as x approaches infinity of 3 to the negative x. It's going to be the same thing, right? But anyway, this is the same thing as the limit as x approaches infinity of 1 over e to the x. Well, e is a positive number, so as x gets large, e to the x blows up, and we get 1 over a big number, which is 0. A similar sort of situation occurs here. We have limit as x approaches negative infinity of 1 over 1 plus x cubed. And again, you can just kind of eyeball this one. This is a small over a big. This also goes to 0. One last thing I want to alert you to. Consider the limit as x approaches infinity of sine of x. Now, if you recall, the graph of sine of x looks something like this. Right? And like it continues that way too. This goes on infinitely. It never converges to a single value as x gets big. It just oscillates between -1 and 1. So, weirdly enough, limit as x approaches infinity of sine of x does not exist. And it's not because it's infinite, but it's because it doesn't converge to a value. It never gets arbitrarily close to a value and then stays there. It always oscillates. Okay? So that's that one. This one's a little bit of a trickier one. I'm just going to ask you to try that one. See how it goes. That's all.